Picture this, a lone planet, untethered from any star, drifting silently through the vast, cold expanse of space. No light to warm it, no orbit to define its path, just an eternal wanderer in the darkness. This isn't science fiction. This is the reality of rogue planets, some of the most enigmatic and mysterious objects in the universe. Today, we're diving deep into the cosmos to uncover 25 specific space mysteries that surround these celestial nomads. From their mysterious origins to the mind-bending questions they raise about life, gravity, and the very fabric of our universe, rogue planets challenge everything we think we know about the cosmos. Why were they cast out from their star systems? Could they harbor life in the freezing void? And what secrets do they hold about the early days of the universe? By the end of this video, you'll not only have a front row seat to some of the most fascinating discoveries in space science, but you'll also walk away with a new perspective on just how strange and wondrous our universe truly is. So buckle up, because we're about to embark on a journey through the unknown, where every discovery is more astonishing than the last. Let's explore the enigma of rogue planets and their origins. Now, let's turn our attention to the first of these cosmic wanderers, a rogue planet we'll call the Lonely Wanderer. Discovered in 2015, this planet made headlines not just for its rogue status, but for its sheer size. Imagine a world nearly 13 times the mass of Jupiter, drifting alone through the void. What makes this planet so fascinating is that it doesn't orbit a star. Instead, it moves freely through space, untethered and independent. The Lonely Wanderer challenges our understanding of how planets form. Traditionally, we think of planets as forming within the swirling disks of gas and dust around young stars. But this rogue planet doesn't fit that mold. Its existence raises questions. Was it born in a star system and then ejected, or did it form on its own like a failed star? Some scientists believe it might have been flung out of its original system due to gravitational interactions with other massive objects. Others suggest it could have formed directly from a collapsing cloud of gas, much like a star, but without enough mass to ignite nuclear fusion. What's even more intriguing is that the Lonely Wanderer isn't completely dark. It emits a faint glow, likely from residual heat left over from its formation. This glow allowed astronomers to detect it, even though it doesn't reflect light from a star. Its atmosphere, rich in methane and water vapor, hints at a complex history and raises the possibility that it might have once been part of a larger system. This rogue planet forces us to rethink the boundaries of planetary science. If planets can form without stars, what does that mean for our understanding of the universe? Could there be countless other rogue planets out there, hidden in the darkness, waiting to be discovered? The Lonely Wanderer is just the beginning of this cosmic mystery, and as we continue our journey, we'll uncover even more astonishing truths about these enigmatic worlds. Next, we'll dive deeper into the mystery of how this rogue planet was ejected from its star system, exploring the forces that could have sent it on its solitary path through the cosmos. Now, let's unravel the mystery of how the Lonely Wanderer ended up on its solitary journey through the cosmos. One of the leading theories suggests that this massive rogue planet was once part of a star system, but a dramatic event sent it hurtling into the void. Gravitational interactions with other massive objects, such as neighboring planets or even passing stars, could have disrupted its orbit. Imagine a cosmic game of billiards where the gravitational pull of one object slingshots another out of its system. This scenario, known as gravitational scattering, is a strong contender for explaining the Lonely Wanderer's ejection. Another possibility is that the planet was involved in a catastrophic collision. In the chaotic early days of its star system, planets and protoplanets may have collided, sending debris flying in all directions. If the Lonely Wanderer was struck by another large object, the force of the impact could have been enough to eject it entirely. This theory gains traction when we consider the planet's size. Its immense mass would have made it a prime target for such collisions. Some scientists also propose that the Lonely Wanderer might have been part of a binary star system where two stars orbit each other. If one of the stars was ejected or disrupted, the planet could have been flung out as well. This scenario highlights the delicate balance of gravitational forces in multi-star systems and how even a small disturbance can have far-reaching consequences. What's fascinating is that these theories aren't mutually exclusive. The Lonely Wanderer's ejection could have been the result of a combination of factors: gravitational interactions, collisions, and the instability of its original system. Each possibility offers a glimpse into the dynamic and often violent processes that shape planetary systems. As we piece together the story of the Lonely Wanderer, we're reminded of just how unpredictable the universe can be. This rogue planet's journey challenges our understanding of planetary formation and evolution, forcing us to consider the many ways a planet can be cast adrift. And as we continue to explore the cosmos, who knows what other rogue worlds we might uncover, each with its own tale of cosmic upheaval. Next, we'll turn our attention to another fascinating rogue planet, a frozen giant that defies expectations and raises new questions about life in the coldest corners of space. Now, let's venture into the icy depths of space to meet the frozen giant, a rogue planet that defies the odds by surviving in the coldest reaches of the cosmos. Unlike the Lonely Wanderer, this massive rogue planet is shrouded in extreme cold, with temperatures so low that they challenge our understanding of how planets can endure in the void of interstellar space. What makes the frozen giant truly remarkable is its ability to sustain an atmosphere despite the harsh conditions. In the absence of a star to provide warmth, the frozen giant relies on its own internal heat and the insulating properties of its thick atmosphere to maintain a stable environment. This atmosphere, composed primarily of hydrogen and helium, acts like a thermal blanket, trapping what little heat the planet generates from its core. Over billions of years, this process has allowed the frozen giant to retain its atmosphere, even as it drifts through the frigid expanse of space. But how does a planet like this generate heat in the first place? One possibility is radioactive decay within its core. Elements like uranium and thorium, which are present in many planetary interiors, release energy as they decay over time. This slow but steady process could provide enough heat to keep the planet's atmosphere from freezing solid. Another theory suggests that gravitational forces acting on the planet's interior might generate heat through friction, much like the way Jupiter's moon Io experiences volcanic activity due to tidal forces. The frozen giant's ability to sustain an atmosphere in such extreme conditions raises intriguing questions about the potential for life in the coldest corners of the universe. While the surface of this rogue planet is far too cold for liquid water, some scientists speculate that subsurface oceans could exist beneath its icy crust. These hidden reservoirs, warmed by the planet's internal heat, might provide a haven for microbial life, much like the oceans beneath the icy shells of moons like Europa and Enceladus. As we study the frozen giant, we gain new insights into the resilience of planets in the harshest environments. Its existence challenges our assumptions about where life might thrive and expands our understanding of planetary survival beyond the warmth of a star. Next, we'll dive deeper into the possibility of hidden oceans on this frozen giant and what they could mean for the search for life in the cosmos. Now, let's take a closer look at what lies beneath the icy surface of the frozen giant. While its exterior is a frozen wasteland, scientists have begun to speculate that this rogue planet might hide something extraordinary beneath its crust: vast subsurface oceans. These hidden reservoirs of liquid water, kept warm by the planet's internal heat, could be one of the most exciting discoveries in the search for life beyond Earth. The idea of subsurface oceans isn't new. We've seen similar environments on moons like Europa and Enceladus, where tidal forces from their parent planets generate enough heat to keep water in liquid form beneath thick layers of ice. The frozen giant, however, doesn't have a star or a nearby planet to provide such warmth. Instead, its heat comes from within, likely generated by radioactive decay or gravitational forces acting on its core. This internal heat could create pockets of liquid water, shielded from the freezing temperatures of space by miles of ice. What makes this possibility so fascinating is the potential for microbial life. On Earth, life thrives in some of the most extreme environments, from deep-sea hydrothermal vents to acidic hot springs. If the frozen giant subsurface oceans exist, they could provide a stable environment with the necessary ingredients for life: liquid water, heat, and organic molecules. While the surface of the planet is inhospitable, these hidden oceans might offer a sanctuary where life could emerge and evolve. The search for these oceans is challenging as they lie far beneath the planet's icy shell. Future missions equipped with advanced radar or seismic instruments could help us peer beneath the surface and detect signs of liquid water. If confirmed, the discovery would revolutionize our understanding of where life can exist in the universe. It would also raise new questions about how life might adapt to such isolated and extreme environments. As we continue to explore the mysteries of rogue planets like the frozen giant, the possibility of hidden oceans reminds us that life might find a way in even the most unexpected places. Next, we'll turn our attention to another enigmatic wanderer, the Dark Wanderer, a rogue planet that emits no light and remains nearly invisible to our telescopes. What secrets does this shadowy traveler hold? Let's find out. Now, shifting our gaze to the shadows of the cosmos, we encounter the Dark Wanderer, a rogue planet unlike any we've explored so far. This mysterious world emits no light, making it nearly invisible to traditional telescopes. Its presence is felt more than seen, a ghostly traveler drifting silently through the void of space. But how do astronomers detect something so elusive? The answer lies in the subtle clues it leaves behind. The Dark Wanderer was first discovered not by its light, but by its gravitational influence. As it passes in front of distant stars, its gravity bends and distorts their light, a phenomenon known as gravitational microlensing. This bending creates a temporary brightening of the star's light, a telltale sign that something massive yet unseen is passing by. It's like spotting the shadow of an invisible giant moving across a lit stage. Through this method, astronomers were able to estimate the planet's mass and distance, piecing together its existence despite its lack of visibility. What makes the Dark Wanderer truly unique is its composition and environment. Unlike other rogue planets that might retain some heat or faint glow from their formation, this one is cold and dark, with no atmosphere to reflect or emit light. Its surface, if it has one, is likely a barren expanse of frozen rock and ice, untouched by the warmth of a star. This extreme darkness raises intriguing questions about how such a planet formed and what processes could have stripped it of any residual heat or light. Adding to its mystery is the possibility that the Dark Wanderer might be influenced by forces beyond our current understanding. Some scientists speculate that dark matter, the invisible substance that makes up a significant portion of the universe, could play a role in shaping its trajectory. While this remains a theory, it opens up fascinating avenues for research into how dark matter interacts with rogue planets and other celestial bodies. As we continue to study the Dark Wanderer, it serves as a reminder of how much we still have to learn about the unseen corners of our galaxy. Its discovery challenges our assumptions about what a planet can be and pushes the boundaries of how we detect and study these cosmic nomads. Next, we'll delve into the story of the Speeding Bullet, a rogue planet racing through the galaxy at incredible speeds. What forces could propel such a world, and what risks does it pose to the cosmos? Let's find out. Now, let's venture deeper into the mystery of the Dark Wanderer and its potential connection to one of the universe's greatest enigmas, dark matter. This invisible substance, which makes up about 85% of the universe's mass, has long puzzled scientists. While we can't see dark matter directly, its gravitational effects are undeniable, shaping the movement of galaxies and even individual celestial bodies. Could it also be influencing the path of rogue planets like the Dark Wanderer? One compelling theory suggests that dark matter might act as an unseen guide, subtly altering the trajectory of rogue planets as they drift through the galaxy. Imagine the Dark Wanderer moving through a vast, invisible web of dark matter. As it passes through regions with higher concentrations of this mysterious substance, its path could be gently nudged or redirected. This interaction, though subtle, might explain why some rogue planets follow unexpected or erratic paths through space. But how could dark matter exert such influence? Scientists propose that dark matter could create localized gravitational hotspots in space. These areas, denser with dark matter, would have a stronger gravitational pull, potentially bending the trajectory of nearby objects. For a rogue planet like the Dark Wanderer, this could mean slight changes in direction or speed over time, steering it away from what we might predict based on visible matter alone. Another intriguing possibility is that dark matter could accumulate around rogue planets, forming a kind of invisible halo. This halo might not only affect the planet's movement but also shield it from other cosmic forces. For instance, it could protect the planet from the gravitational pull of nearby stars or even deflect high-energy particles that might otherwise strip away any remaining atmosphere. While this remains speculative, it opens up fascinating questions about how dark matter interacts with isolated worlds. Of course, these theories are still in their early stages, and much about dark matter remains unknown. Detecting its influence on rogue planets is no easy task, as it requires precise measurements of their movements over long periods. Yet, the very idea that dark matter could play a role in shaping the journey of these cosmic nomads adds another layer of intrigue to their story. As we continue to explore the Dark Wanderer and its possible connection to dark matter, we're reminded of how much of the universe remains hidden from our view. Every discovery brings new questions, and every question pushes us closer to understanding the unseen forces that govern our cosmos. Next, we'll turn our attention to the speeding bullet, a rogue planet racing through the galaxy at astonishing speeds. What could propel such a world, and what dangers might it pose to the stars and planets in its path? Let's dive in. Now, let's shift our focus to a rogue planet that defies expectations with its sheer speed, the speeding bullet. This cosmic traveler is racing through the galaxy at an astonishing pace, leaving astronomers both amazed and puzzled. What could have set this rogue planet in motion, and what does its incredible velocity mean for the cosmos? The speeding bullet's journey begins with a dramatic event, its ejection from its original star system. Imagine a young planetary system, still chaotic and unstable, where gravitational tugs of war between massive planets or passing stars can fling smaller worlds into the void. In the case of the speeding bullet, it's possible that a close encounter with a gas giant or a nearby star provided the gravitational slingshot needed to send it hurtling into interstellar space. This kind of ejection isn't just a gentle push, it's a violent, high-energy event that can propel a planet to incredible speeds. But the speeding bullet's story doesn't end there. Once ejected, it continues to accelerate as it travels through the galaxy. One theory suggests that the planet might have passed near other massive objects, such as black holes or dense star clusters, which could have further boosted its speed through gravitational interactions. Over millions or even billions of years, these encounters could have turned the speeding bullet into one of the fastest rogue planets ever observed. The implications of such a high-speed rogue planet are both fascinating and concerning. On one hand, its velocity makes it a unique object of study, offering insights into the extreme forces at play in the universe. On the other hand, its speed also makes it a potential hazard. If the speeding bullet were to pass close to another star system, Its gravitational influence could disrupt the orbits of planets or even send comets and asteroids hurtling inward, posing a threat to any potential life. What's more, the speeding bullet's journey raises questions about the fate of other rogue planets. Could there be more of these high-speed wanderers out there, silently racing through the galaxy? And if so, what does that mean for the stability of star systems they might encounter? While the chances of a direct collision are slim, the gravitational ripple effects of such encounters could have lasting consequences. As we ponder the mysteries of the speeding bullet, we're reminded of the dynamic and ever-changing nature of our universe. Rogue planets like this one challenge our understanding of planetary motion and remind us that the cosmos is full of surprises. Next, we'll explore the dangers posed by these high-speed travelers and the potential risks they bring to the star systems they encounter. Stay tuned as we uncover more about the cosmic dance of rogue planets and their impact on the galaxy. Now, let's take a closer look at the potential dangers these high-speed rogue planets bring to the galaxy. The speeding bullet, with its incredible velocity, isn't just a fascinating cosmic anomaly. It's also a reminder of the risks that come with such fast-moving objects. When a rogue planet like this travels through space, it doesn't just drift quietly. Its immense gravitational pull can have a significant impact on anything in its path. Imagine a rogue planet passing near a stable star system. Even if it doesn't collide directly with any planets, its gravitational influence could still wreak havoc. The speeding bullet's gravity might tug on the orbits of planets, moons, or even asteroids, causing them to shift slightly or dramatically. Over time, these small changes could destabilize entire systems, potentially sending planets spiraling out of their orbits or triggering a cascade of collisions among smaller objects like comets and asteroids. One of the most concerning scenarios is the possibility of a rogue planet passing through a star system's Oort cloud, a vast region of icy bodies at the outer edges of the system. The gravitational disturbance caused by the rogue planet could send these icy objects hurtling inward, creating a storm of comets that might bombard inner planets. For a system like ours, this could pose a serious threat to life, as such impacts could alter climates, trigger mass extinctions, or even sterilize a planet entirely. But the risks don't stop there. In rare cases, a rogue planet could come close enough to a star to disrupt its planetary disk, the ring of dust and debris that often surrounds young stars. This disruption could prevent new planets from forming or scatter existing ones, altering the fate of an entire system before it even has a chance to stabilize. The speeding bullet, with its incredible speed, could pass through multiple systems over its lifetime, leaving a trail of gravitational chaos in its wake. Of course, the likelihood of such catastrophic encounters is relatively low given the vastness of space, but the fact that these events are possible at all highlights the unpredictable nature of rogue planets. They remind us that the universe is a dynamic and sometimes dangerous place, where even the smallest gravitational nudge can have far-reaching consequences. As we consider the dangers posed by rogue planets like the speeding bullet, we're left with a deeper appreciation for the delicate balance that allows star systems to thrive. Next, we'll turn our attention to another intriguing rogue planet, one with a magnetic field so strong it defies expectations. Stay with us as we explore how this magnetic anomaly could hold clues to the survival of rogue planets in the harsh environment of interstellar space. Now, shifting our focus to another fascinating rogue planet, we encounter a true cosmic oddity, a world with a magnetic field so powerful it stands out even among the most unusual objects in the galaxy. This rogue planet, which we'll call the magnetic anomaly, challenges our understanding of what's possible in the realm of planetary science. Unlike most rogue planets, which drift through space without the protection of a star, this one boasts a magnetic field strong enough to shield it from the harsh environment of interstellar space. So, what makes this magnetic field so extraordinary? For starters, it's far stronger than what we see on Earth or even on gas giants like Jupiter. This intense magnetic field acts like a cosmic force field, deflecting harmful cosmic radiation and charged particles that would otherwise bombard the planet's surface. For a rogue planet, this is a game changer. Without a star to provide warmth or protection, these wandering worlds are typically exposed to the full brunt of space's dangers. But the magnetic anomaly's magnetic field offers a layer of defense, potentially making it one of the most resilient rogue planets we've ever discovered. This raises an intriguing question. Could this magnetic field make the planet more habitable? While rogue planets are often thought of as cold, lifeless worlds, the magnetic anomaly's unique feature opens up new possibilities. If the planet has any internal heat sources, such as radioactive decay or residual warmth from its formation, the magnetic field could help retain that heat, creating a more stable environment. Combined with the shielding from radiation, this could create conditions where microbial life or even more complex organisms might survive. But how does a rogue planet develop such a strong magnetic field in the first place? The answer likely lies in its core. Planets generate magnetic fields through the movement of molten metals in their interiors, a process known as a dynamo effect. For the magnetic anomaly, this suggests a core that's not only massive but also highly active, possibly containing a unique mix of elements that enhance its magnetic properties. Understanding this process could give us clues about how other rogue planets might develop similar features, or even how magnetic fields evolve in more traditional planetary systems. As we continue to study the magnetic anomaly, it's clear that this rogue planet is more than just a curiosity. It's a window into the diverse and unexpected ways planets can adapt to the challenges of interstellar space. Next, we'll delve deeper into the mysteries of this planet's magnetic field, exploring the theories behind its origins and what it might mean for the future of rogue planet research. Stay tuned as we uncover more about this magnetic marvel and its place in the cosmos. Now, let's take a closer look at what might be powering the magnetic anomaly's incredible magnetic field. The key to this mystery likely lies deep within the planet's core. On Earth, our magnetic field is generated by the movement of molten iron and nickel in the outer core, a process known as the dynamo effect. But for the magnetic anomaly, the story seems to be far more complex. Scientists believe this rogue planet's core could be composed of an unusual mix of elements, possibly including heavy metals like uranium or thorium, which are known for their radioactive properties. These elements could generate immense heat as they decay, keeping the core molten and driving the dynamo effect to extraordinary levels. Another theory suggests that the planet's core might not be entirely metallic. Instead, it could contain layers of exotic materials such as superionic water or metallic hydrogen, which behave differently under extreme pressures. These materials could create a more efficient dynamo, producing a magnetic field far stronger than anything we've seen in our own solar system. Some researchers even speculate that the planet's core might have been altered by a massive collision in its early history, leaving behind a dense, highly conductive material that amplifies its magnetic properties. But what's truly fascinating is how this magnetic field could have formed in the first place. Unlike planets in star systems, rogue planets don't have the gravitational influence of a star to shape their interiors. This means the magnetic anomaly's core must have developed its unique composition entirely on its own, possibly through a combination of its initial formation conditions and the extreme pressures of interstellar space. Understanding this process could give us valuable insights into how planetary cores evolve in the absence of a star, and whether other rogue planets might also possess similar magnetic fields. As we piece together the clues about the magnetic anomaly's core, one thing becomes clear: this planet is rewriting the rules of planetary science. Its magnetic field isn't just a curiosity, it's a testament to the incredible diversity of worlds that exist in the cosmos. Next, we'll explore how this magnetic marvel might influence our search for life beyond our solar system, and what it tells us about the potential for habitable environments on rogue planets. Stay with us as we continue to unravel the secrets of this magnetic wanderer and its place in the universe. Now, let's turn our attention to a rogue planet that stands as a cosmic time capsule, a relic from the earliest days of the universe. Known as the Ancient Relic, this rogue planet is believed to be one of the oldest in the galaxy, offering us a rare glimpse into the conditions that shaped the cosmos billions of years ago. Its age alone makes it a treasure trove of information, but what exactly does this ancient wanderer tell us about the universe's infancy? The Ancient Relic is thought to have formed during a period when the universe was still in its youth, a time when the first stars and planets were just beginning to take shape. Unlike planets that formed later, this rogue planet likely emerged from a primordial soup of elements: hydrogen, helium, and trace amounts of heavier elements forged in the hearts of the earliest stars. Its composition could hold clues about the chemical makeup of the early universe, shedding light on how the building blocks of planets and stars evolved over time. One of the most intriguing aspects of the Ancient Relic is its potential to reveal how planetary systems formed in the absence of the complex structures we see today. In the early universe, star systems were less crowded and gravitational interactions were less chaotic. This means the Ancient Relic might have formed in a simpler, more isolated environment, free from the gravitational tug of war that often ejects planets from their systems. Its survival as a rogue planet suggests it was either born in solitude or ejected very early in its history, preserving its ancient characteristics. But what makes this planet truly special is its potential to carry traces of the universe's first elements. Scientists speculate that its surface or interior could contain primordial materials that have remained unchanged for billions of years. These materials could include isotopes or compounds that no longer exist in younger planets, offering a direct link to the universe's earliest moments. Studying the Ancient Relic could help us understand how the first planets formed, what conditions were like in the early galaxy, and even how life's essential elements came to be. As we continue to explore this ancient wanderer, one question looms large. Could the Ancient Relic hold the key to unlocking the secrets of planetary formation in the early universe? Its age and isolation make it a unique laboratory for studying the cosmos's origins, and its discovery reminds us just how much we still have to learn about the universe's history. Next, we'll delve into the search for these primordial elements and what they could mean for our understanding of cosmic evolution. Stay with us as we uncover more about this extraordinary time traveler and its place in the grand story of the universe. Now, let's take a closer look at what makes the Ancient Relic so extraordinary: the possibility of finding primordial elements hidden within its ancient structure. These elements, remnants from the universe's earliest days, could hold the key to understanding how the cosmos evolved from a chaotic, elemental soup into the structured galaxy we see today. Imagine uncovering materials that have remained untouched for billions of years, offering a direct window into the universe's infancy. What secrets might they reveal? Scientists believe that the Ancient Relic could contain isotopes and compounds that no longer exist in younger planets. These primordial elements, forged in the hearts of the first stars, would provide invaluable insights into the chemical makeup of the early universe. For instance, finding traces of hydrogen and helium in their purest forms could help us understand how these elements combined to form the first molecules, setting the stage for the birth of stars and planets. Even more intriguing is the possibility of discovering heavier elements like lithium or beryllium, which were among the first to form after the Big Bang. These elements could tell us about the processes that shaped the universe's earliest structures. But why are these primordial elements so important? They act as cosmic fingerprints, preserving the conditions of the universe as it was billions of years ago. By studying them, we can piece together the timeline of cosmic evolution, from the formation of the first atoms to the creation of complex molecules. This ancient planet, with its untouched materials, serves as a time capsule, offering a rare opportunity to study the universe's building blocks in their original state. It's like finding a perfectly preserved artifact from a long-lost civilization, except this artifact is billions of years old and holds the secrets of the cosmos itself. One of the most exciting prospects is the potential to uncover clues about how life's essential elements came to be. Elements like carbon, nitrogen, and oxygen, which are crucial for life as we know it, were not present in the early universe. They were created later through the life cycles of stars. By studying the ancient relic, we might gain a better understanding of how these elements formed and spread throughout the galaxy, eventually making life possible. Could this ancient planet hold the missing link in the story of how life's building blocks came to exist? As we continue to explore the ancient relic, the search for these primordial elements becomes more than just a scientific endeavor. It's a journey into the very origins of the universe. Each discovery brings us closer to understanding how the cosmos transformed from a sea of simple elements into the complex, dynamic galaxy we inhabit today. Next, we'll shift our focus to another fascinating rogue planet, one that challenges our understanding of planetary systems in a completely different way. Stay tuned as we uncover more mysteries of these cosmic wanderers. Now, let's turn our attention to a truly unique phenomenon in the cosmos, the binary rogue. Imagine two rogue planets untethered from any star, locked in a gravitational dance as they drift through the vast emptiness of space. This rare pairing challenges our understanding of planetary systems and offers a fascinating glimpse into the complex dynamics of gravity in the universe. The formation of a binary rogue system is a cosmic puzzle. One leading theory suggests that these planets were once part of a larger star system, where gravitational interactions, perhaps from a passing star or a collision, ejected them together. Instead of drifting apart, their mutual gravitational pull kept them bound, creating a binary system. Another possibility is that they formed independently in a dense region of space, where their close proximity allowed gravity to link them in a shared orbit. Regardless of how they came to be, their existence raises intriguing questions about the stability and resilience of such systems in the harsh environment of interstellar space. What makes binary rogue planets so fascinating is what they reveal about gravitational dynamics. Unlike planets orbiting a star, these two worlds rely solely on each other's gravity to maintain their connection. This delicate balance requires precise conditions, neither too close to collide nor too far to drift apart. Studying these systems helps scientists understand how gravitational forces operate in isolation without the influence of a central star. It also sheds light on how planetary systems can evolve and adapt under extreme conditions. The stability of binary rogue planets is another area of interest. While their mutual gravity keeps them together, external forces like the gravitational pull of passing stars or the tidal forces of the galaxy could disrupt their orbit over time. Yet, some binary systems may survive for billions of years, enduring the chaotic environment of space. This resilience offers clues about the long-term fate of such systems and their potential to influence the formation of other celestial bodies. As we explore the mysteries of the binary rogue, we gain a deeper appreciation for the intricate dance of gravity that shapes our universe. These rare pairs remind us that even in the vast emptiness of space, connections can form and worlds can find companionship. Next, we'll delve into the stability of binary systems and what their survival tells us about the cosmos. Stay with us as we continue to unravel the secrets of these extraordinary cosmic wanderers. Now, let's take a closer look at the stability of binary rogue planets and what it means for their survival over billions of years. These cosmic duos, bound only by their mutual gravity, face a unique set of challenges as they drift through the galaxy. Unlike planets orbiting a star, binary rogue systems lack the stabilizing influence of a central gravitational anchor. Instead, their survival depends on the delicate balance between their own gravitational pull and the external forces acting upon them. One of the key factors influencing their stability is the distance between the two planets. If they're too close, their gravitational interaction could lead to collisions or tidal forces that disrupt their orbits. On the other hand, if they're too far apart, the pull of passing stars or galactic tides might eventually tear them apart. This delicate equilibrium makes binary rogue systems a fascinating subject for astronomers, as they offer insights into how gravitational bonds can endure in the chaotic environment of interstellar space. Another factor to consider is the role of external influences. As these binary systems travel through the galaxy, they encounter gravitational forces from nearby stars, molecular clouds, and even the overall tidal pull of the Milky Way. These interactions can either strengthen or weaken their bond, depending on the circumstances. For instance, a close encounter with a massive star might provide enough energy to disrupt their orbit, while a gentler interaction could leave them unscathed. Over time, these cumulative effects determine whether a binary system remains intact or drifts apart. Interestingly, some binary rogue planets may have the potential to survive for billions of years, outlasting even the stars they once orbited. Their resilience lies in their ability to adapt to changing conditions, maintaining their gravitational connection despite the challenges they face. This longevity offers valuable clues about the formation and evolution of planetary systems, as well as the broader dynamics of the galaxy. By studying these systems, scientists can better understand how celestial bodies interact and evolve over cosmic timescales. As we reflect on the stability of binary rogue planets, we're reminded of the incredible forces at play in the universe. These systems, though rare, provide a unique window into the complexities of gravity and the enduring nature of cosmic connections. Next, we'll explore another intriguing aspect of rogue planets, those that defy expectations with their surprising heat. Stay tuned as we uncover the mysteries of the hot rogue and the secrets it holds. Now, let's turn our attention to a rogue planet that challenges everything we thought we knew about these cosmic wanderers, the hot rogue. Unlike the icy, desolate worlds we've explored so far, this rogue planet boasts a surprisingly high surface temperature, defying the typical image of a cold, dark object drifting through space. So, what makes this planet so hot, and where does its heat come from? One of the most fascinating aspects of the hot rogue is its internal heat sources. While most rogue planets lose their heat over time, this one seems to have found a way to stay warm. One possibility is that it's still cooling down from its formation, retaining heat from the intense pressures and temperatures that shaped it billions of years ago. Another theory suggests that radioactive elements within its core could be generating heat through decay, much like the process that keeps Earth's interior warm. This internal warmth could explain why the planet's surface remains surprisingly hot, even in the frigid depths of interstellar space, but that's not all. The hot rogue might also be generating heat through tidal forces. If it has a moon or is part of a binary system, the gravitational tug of war between the two bodies could create friction within the planet, producing additional heat. This process, known as tidal heating, is similar to what happens on Jupiter's moon Io, which is one of the most volcanically active bodies in our solar system. If the hot rogue is experiencing something similar, it could explain why it's so much warmer than other rogue planets. Another intriguing possibility is that the hot rogue is still young, relatively speaking. If it was ejected from its star system recently, it might not have had enough time to cool down completely. This would make it a rare example of a rogue planet caught in the early stages of its journey through the galaxy, offering scientists a unique opportunity to study how these worlds evolve over time. What's truly remarkable about the hot rogue is how it defies our expectations. Rogue planets are often thought of as cold, lifeless worlds, but this one challenges that notion, showing us that there's still so much we don't understand about these enigmatic objects. Its heat could even raise questions about the potential for habitability. Could a rogue planet like this one, with its internal warmth, support liquid water or even life? While it's a long shot, the possibility is enough to spark curiosity and drive further exploration. As we ponder the mysteries of the hot rogue, we're reminded once again of the incredible diversity of rogue planets. Each one tells a unique story, offering clues about the forces that shape our universe. Next, we'll delve into the role of radioactive decay in sustaining the heat of rogue planets like this one, uncovering even more secrets about these fascinating cosmic wanderers. Stay tuned as we continue our journey through the enigma of rogue planets. Now, let's take a closer look at what might be fueling the heat of the hot rogue. One of the most compelling explanations lies deep within its core radioactive decay. Just like Earth, this rogue planet could be generating heat through the natural breakdown of radioactive elements like uranium, thorium, and potassium. These elements trapped within the planet's interior release energy as they decay over time, creating a steady source of warmth that defies the cold void of space. This process isn't just theoretical. On Earth, radioactive decay plays a significant role in keeping our planet's core hot, driving geological activity like volcanoes and plate tectonics. If the hot rogue has a similar composition, it could mean that its core is still active, producing enough heat to maintain its surprisingly high surface temperature. This would make it one of the few known rogue planets with an internal heat source, challenging the idea that these worlds are entirely cold and inert. But how long could this heat last? Radioactive elements have half-lives that span millions or even billions of years, meaning the hot rogue could remain warm for an incredibly long time. This raises fascinating questions about its lifespan and evolution. Could it eventually cool down, or would its radioactive core keep it warm indefinitely? The answer could depend on the planet's size, composition, and the specific elements present in its core. What's even more intriguing is the potential implications for habitability. If the hot rogue's heat is sustained by radioactive decay, it might create conditions suitable for liquid water beneath its surface. While the surface itself would likely be inhospitable, the warmth from its core could maintain subsurface oceans, much like those suspected to exist on moons like Europa and Enceladus. This opens up the tantalizing possibility that rogue planets, long thought to be barren, could harbor environments where life might thrive. As we explore the role of radioactive decay in rogue planets, we're reminded of how much we still have to learn about these mysterious worlds. Each discovery challenges our assumptions and expands our understanding of the universe. Next, we'll shift our focus to another fascinating rogue planet, the miniature rogue, and explore how its small size is rewriting the rules of planetary classification. Stay with us as we continue to unravel the enigma of rogue planets. Now, let's turn our attention to a rogue planet that defies expectations with its diminutive size, the miniature rogue. Unlike the massive, icy giants we've explored so far, this planet is surprisingly small, possibly even a super-Earth. Its compact size challenges our traditional understanding of what a rogue planet can be, forcing us to rethink how we classify these wandering worlds. Typically, rogue planets are imagined as colossal, Jupiter-like bodies drifting through the void. But the miniature rogue shatters that stereotype. With a size closer to Earth's, it raises intriguing questions about how such a small planet could survive the harsh conditions of interstellar space. How did it form? Was it ejected from a star system, or did it emerge independently in the vast expanse of the galaxy? These questions push the boundaries of planetary science and invite us to reconsider the diversity of rogue planets. The discovery of the miniature rogue also highlights the limitations of our current classification systems. Traditionally, planets are categorized based on their size, composition, and relationship to a star. But rogue planets, especially ones as small as this, blur those lines. Is it still a planet if it doesn't orbit a star, or does its size and composition place it in a new category altogether? These debates are reshaping how astronomers define and study planetary bodies, opening up new avenues for exploration. What's particularly fascinating about the miniature rogue is its potential to teach us about planetary formation on a smaller scale. If it's a super-Earth, it could have a rocky composition similar to our own planet, but without the protection of a star, it faces unique challenges. How does it retain its atmosphere if it has one? Could its small size make it more vulnerable to cosmic radiation or gravitational disruptions? These are just some of the mysteries that make this tiny wanderer so compelling. As we delve deeper into the story of the miniature rogue, we're reminded that the universe is full of surprises. Its existence challenges our assumptions and expands our understanding of what's possible in the cosmos. Next, we'll explore another intriguing aspect of this small rogue planet: its potential for life. Could this tiny world, adrift in the darkness, harbor the conditions necessary for life to exist? Stay with us as we continue to uncover the secrets of rogue planets. Now, let's shift our focus to one of the most tantalizing questions surrounding the miniature rogue. Could this small, wandering world harbor life? While the idea of life existing on a rogue planet might seem far-fetched, the unique characteristics of this tiny wanderer make it a fascinating subject for speculation. Its size, composition, and potential for liquid water all play a role in this intriguing possibility. First, let's consider its size. Being a super-Earth, the miniature rogue likely has a rocky composition, similar to our own planet. This raises the possibility that it could have a solid surface, which is a key ingredient for life as we know it. But without the warmth of a nearby star, how could life survive? One theory suggests that the planet might retain heat from its formation or through the decay of radioactive elements in its core. This internal heat could create pockets of warmth beneath its surface, potentially allowing for liquid water to exist in subsurface oceans. Speaking of water, let's explore that further. Water is essential for life, and the presence of liquid water, even in hidden reservoirs, could make the miniature rogue a candidate for microbial life. If the planet has a thick, icy crust, it might trap heat and create conditions where water remains liquid beneath the surface. This scenario is similar to what scientists believe might exist on moons like Europa or Enceladus in our own solar system. Could the miniature rogue be hiding a similar secret? Another factor to consider is the planet's atmosphere, or lack thereof. Without a star to provide energy, maintaining an atmosphere would be incredibly challenging. However, if the miniature rogue has a strong magnetic field, it could protect any atmosphere it has from being stripped away by cosmic radiation. This magnetic shield, combined with internal heat, might create a stable environment where life could potentially thrive, even in the absence of sunlight. Of course, the idea of life on a rogue planet is still speculative, but it's a possibility that excites scientists and space enthusiasts alike. The miniature rogue challenges us to think beyond the traditional boundaries of habitability. Could life exist in the cold, dark depths of interstellar space? If so, what forms might it take? These questions push the limits of our imagination and remind us that the universe is full of surprises. As we ponder the potential for life on this small rogue planet, we're reminded of how much we still have to learn about the cosmos. The miniature rogue is not just a scientific curiosity, it's a window into the incredible diversity of planetary systems and the possibilities they hold. Next, we'll explore another fascinating rogue planet, one that moves through the galaxy with an erratic and unpredictable path. Stay tuned as we continue our journey through the mysteries of rogue planets. Now, let's turn our attention to a rogue planet that defies the norm with its chaotic journey through the cosmos, the cosmic nomad. Unlike most rogue planets that drift in relatively straight paths, this wanderer follows an erratic orbit, weaving through different regions of the galaxy. Its unpredictable trajectory raises fascinating questions about the forces that shape its movement and the potential consequences of its restless journey. The cosmic nomad's erratic path is likely influenced by a combination of gravitational interactions and cosmic forces. As it travels, it may pass close to massive objects like stars, black holes, or dense star clusters, each encounter tugging it in a new direction. This gravitational tug-of-war creates a path that is anything but straightforward, making it one of the most dynamic rogue planets we've discovered. But what does this mean for the planet itself and for the regions it passes through? One of the most intriguing implications of the cosmic nomad's journey is its potential to disrupt other star systems. As it moves through the galaxy, it could come close enough to a star system to disturb the orbits of planets or even eject smaller bodies into interstellar space. While the chances of a direct collision are slim, the gravitational influence of such a massive object could have lasting effects on the stability of nearby systems. This raises the question, could rogue planets like this one play a role in shaping the architecture of the galaxy over time? Another aspect to consider is the planet's own survival. Traveling through such varied environments exposes the cosmic nomad to extreme conditions, from intense radiation near stars to the frigid void of interstellar space. How does it endure these challenges? Some scientists speculate that its thick atmosphere or strong magnetic field might shield it from the harshest effects, allowing it to persist despite its tumultuous journey. Others suggest that its erratic path could even provide opportunities for it to capture material or energy from the regions it passes through, sustaining itself in unexpected ways. The cosmic nomad also offers a unique perspective on the diversity of rogue planets. While many are solitary wanderers, this planet's dynamic orbit highlights the complexity of their origins and behaviors. It challenges us to rethink our assumptions about how rogue planets move and interact with their surroundings, reminding us that the universe is full of surprises. As we reflect on the cosmic nomad's unpredictable journey, we're reminded of the ever-changing nature of the cosmos. Its path is a testament to the powerful forces at work in the galaxy, shaping not only its own destiny but potentially influencing the fate of other worlds. Next, we'll explore another enigmatic rogue planet, one that stands out for its lack of atmosphere and what that reveals about planetary evolution. Stay with us as we continue to unravel the mysteries of these cosmic wanderers. Now, let's take a closer look at the forces that guide the cosmic nomad on its unpredictable journey through the galaxy. Galactic tides, the subtle but powerful gravitational effects exerted by the Milky Way itself, play a significant role in shaping the path of this wandering planet. These tides are created by the uneven distribution of mass within the galaxy, from its dense core to its sprawling spiral arms. As the cosmic nomad moves through these regions, it experiences a constant push and pull, subtly altering its trajectory over time. In addition to galactic tides, other cosmic forces come into play. The gravitational influence of nearby stars, star clusters, and even dark matter can nudge the planet in unexpected directions. Imagine the galaxy as a vast, interconnected web of gravitational interactions, with the cosmic nomad caught in its intricate threads. Each encounter with a massive object, no matter how brief, leaves a mark on the planet's path, contributing to its erratic orbit. One fascinating aspect of these forces is their ability to accelerate or decelerate the planet as it travels. For instance, passing close to a dense star cluster might give the cosmic nomad a gravitational boost, sending it hurtling toward a new region of the galaxy. Conversely, a close encounter with a massive black hole could slow it down, altering its speed and direction in dramatic ways. These interactions highlight the dynamic nature of the galaxy and the complex dance of forces that govern the movement of rogue planets. The cosmic nomad's journey also raises questions about the long-term effects of these forces. Over millions or even billions of years, the cumulative impact of galactic tides and gravitational interactions could significantly alter its path. Some scientists speculate that such forces might eventually steer the planet toward a new star system, where it could be captured and become part of a planetary family once again. Others suggest it might continue its solitary journey indefinitely, forever shaped by the invisible hands of the galaxy. As we consider the influence of these cosmic forces, we gain a deeper appreciation for the interconnectedness of the universe. The cosmic nomad's path is not just a random series of movements, but a reflection of the intricate balance of forces that shape the cosmos. Its journey reminds us that even the most solitary objects in space are part of a larger, dynamic system, constantly influenced by the galaxy around them. With this understanding, we're ready to explore another intriguing rogue planet, one that stands out for its complete lack of atmosphere, and what that reveals about the evolution of planets in the harsh environment of interstellar space. Stay with us as we continue to uncover the secrets of these enigmatic wanderers. Now, let's turn our attention to a rogue planet that stands out for its eerie silence, the silent observer. Unlike most planets, this wanderer appears to have no atmosphere at all, making it a truly unique object in the vast expanse of interstellar space. Without the protective blanket of gases that typically surround planets, the silent observer is exposed to the harsh conditions of the cosmos, offering us a rare glimpse into the extremes of planetary evolution. The absence of an atmosphere raises intriguing questions about how this planet came to be. One possibility is that it once had an atmosphere, but over time, it was stripped away by intense radiation or powerful stellar winds from nearby stars. Another theory suggests that the silent observer may have formed in a region of space where the materials needed to create an atmosphere were scarce, leaving it bare from the start. Whatever the cause, its lack of atmosphere makes it a fascinating subject for study, as it challenges our understanding of how planets form and evolve. What makes the silent observer even more remarkable is what its condition reveals about the survival of planets in the void of space. Without an atmosphere to trap heat or shield it from cosmic radiation, this planet exists in a state of perpetual cold and exposure. Its surface, if it has one, would be a barren, frozen landscape, untouched by the processes that shape atmosphered worlds. Yet, despite these harsh conditions, the silent observer persists, a testament to the resilience of planetary bodies in the most unforgiving environments. This rogue planet also provides valuable insights into the diversity of planetary systems. Its existence suggests that not all planets follow the same evolutionary path. Some may lose their atmospheres due to external forces, while others may never develop one at all. By studying the silent observer, scientists can better understand the range of possibilities for planetary formation and the factors that determine a planet's fate. As we reflect on the silent observer's stark existence, we're reminded of the incredible variety of worlds that populate our galaxy. Its story is one of survival and adaptation, offering a window into the extremes of planetary life. And as we continue our journey through the mysteries of rogue planets, we'll next explore the long-term fate of planets like the silent observer and their role in the cosmic tapestry. Stay with us as we uncover more secrets of these enigmatic wanderers. Now, let's consider what lies ahead for planets like the silent observer, those that drift through space without the protection of an atmosphere. Over time, these atmosphere-less worlds face a unique set of challenges that shape their ultimate destiny. Without an atmosphere to shield them, they are constantly bombarded by cosmic radiation and micrometeoroids, which can erode their surfaces and alter their composition. This relentless exposure means that these planets may slowly lose material, becoming smaller and more barren as the eons pass. But the story doesn't end there. Despite their harsh conditions, atmosphere-less planets play a surprising role in the galaxy. They act as cosmic time capsules, preserving clues about the early universe and the processes that shaped planetary systems. For example, their surfaces might hold ancient minerals or compounds that have long since disappeared from atmosphered worlds. By studying these relics, scientists can piece together the history of planetary formation and the forces that have shaped the cosmos over billions of years. Another intriguing possibility is that these planets could serve as waypoints for future interstellar exploration. Their lack of atmosphere makes them easier to land on and study, as there's no need to navigate through thick layers of gas or extreme weather conditions. This could make them ideal candidates for robotic missions or even temporary bases for human explorers venturing into the depths of space. Imagine a future where these silent wanderers become stepping stones for humanity's journey to the stars. Yet, the fate of atmosphere-less planets also raises questions about the broader role of such worlds in the galaxy. Could they be more common than we think? And if so, what does that mean for our understanding of planetary systems? Their existence challenges the idea that all planets must follow a similar evolutionary path, reminding us that the universe is full of surprises. As we continue to explore the cosmos, these enigmatic worlds will undoubtedly reveal even more secrets about the diversity and resilience of planetary bodies. As we move forward in our exploration of rogue planets, we'll next turn our attention to a wanderer that defies expectations in a different way, a rogue planet that emits a faint glow, hinting at its mysterious past. Stay with us as we uncover the story of the glowing wanderer and what it tells us about the hidden lives of these cosmic nomads. Now, let's shift our gaze to a rogue planet that stands out in the darkness of space, not because of its size or speed, but because of a faint, mysterious glow. This is the glowing wanderer, a rogue planet that emits a subtle light, a remnant of its fiery past. Unlike most rogue planets which are shrouded in darkness, this one offers a rare glimpse into the hidden lives of these cosmic nomads. The glow of this planet comes from residual heat, a leftover from its formation or perhaps from a violent event in its history. Imagine a piece of coal cooling in the night, still radiating warmth long after the fire has died. That's what this planet is like, a once hot world slowly losing its heat as it drifts through the cold void of interstellar space. But how did astronomers detect such a faint glow? The answer lies in advanced infrared telescopes, which can pick up the subtle heat signatures that visible light telescopes might miss. These instruments act like cosmic thermometers, allowing scientists to see the warmth of distant objects that would otherwise remain invisible. What does this glow tell us about the glowing wanderer's history? For one, it suggests that this planet was once much hotter, possibly part of a star system where it absorbed energy from its parent star. Over time, it may have been ejected, leaving it to cool in the vastness of space. The rate at which it's losing heat can also provide clues about its composition. A planet with a dense metallic core, for example, might retain heat longer than one made mostly of rock or ice. By studying this cooling process, scientists can piece together the planet's internal structure and even estimate its age. But the glowing wanderer isn't just a relic of the past, it's also a window into the future. As it continues to cool, its glow will fade, eventually disappearing entirely. This process offers a rare opportunity to study the life cycle of rogue planets, from their fiery beginnings to their cold, dark ends. It's a reminder that even in the emptiness of space, nothing stays the same forever. As we ponder the fate of the glowing wanderer, we're reminded of the incredible diversity of rogue planets and the stories they hold. Each one is a piece of the cosmic puzzle, helping us understand the forces that shape our universe. And as we continue our journey through these space mysteries, we'll next explore a rogue planet that challenges our understanding of planetary systems in an entirely different way. Stay tuned as we uncover the secrets of the cosmic outcast and its dramatic journey through the galaxy. Now, let's take a closer look at the cooling process of the glowing wanderer and what it tells us about the lifespan of rogue planets. As this planet drifts through the cold expanse of space, its faint glow is gradually fading, a sign that it's losing its residual heat over time. This cooling process is like watching a candle slowly burn out, Each moment brings it closer to darkness, but also reveals something new about its nature. The rate at which the glowing wanderer is cooling provides valuable clues about its composition and internal structure. For instance, a planet with a dense metallic core would retain heat much longer than one made primarily of lighter materials like rock or ice. By studying how quickly its glow diminishes, scientists can estimate the planet's age and even infer what it might be made of. This information helps us understand not just this particular rogue planet, but also the broader life cycle of these cosmic wanderers. What's fascinating is that this cooling process isn't uniform. Some parts of the planet might cool faster than others, depending on their composition and how heat is distributed internally. This uneven cooling can create unique geological features, such as cracks or ridges, as the planet's surface contracts over time. It's a slow, almost imperceptible transformation, but one that offers a glimpse into the dynamic nature of even the coldest, most isolated worlds. As the glowing wanderer continues to cool, it serves as a reminder of the inevitable fate of all rogue planets. Over billions of years, even the faintest glow will fade, leaving these worlds as dark, silent travelers in the void. Yet, this process also highlights the incredible resilience of these planets. Despite being cast adrift from their star systems, they endure, carrying the secrets of their origins and evolution across the galaxy. The story of the glowing wanderer's cooling process is more than just a tale of fading light. It's a window into the life and death of rogue planets. And as we move forward, we'll explore another rogue planet whose journey through the cosmos challenges our understanding of planetary systems in a completely different way. Stay with us as we uncover the mysteries of the cosmic outcast and its dramatic path through the stars. Now, let's turn our attention to a rogue planet with a story as dramatic as it is mysterious, the cosmic outcast. This planet, unlike many of its wandering counterparts, is believed to have been violently ejected from a young star system, setting it on a solitary journey through the cosmos. But what could have caused such a dramatic expulsion? The answer lies in the chaotic early days of planetary formation. In the turbulent environment of a young star system, planets are still jostling for stable orbits. Gravitational interactions between massive planets, or even close encounters with passing stars, can fling a planet out of its system entirely. For the cosmic outcast, this likely happened during a period of intense instability, when the gravitational pull of a larger planet or a nearby star disrupted its orbit. Imagine a game of cosmic billiards where one wrong move sends a planet hurtling into the void, never to return. Once ejected, the cosmic outcast began its lonely voyage through interstellar space. Without the warmth of a star, it quickly cooled, its surface freezing over as it drifted further from its birthplace. Yet this planet's journey is far from uneventful. As it travels, it encounters the gravitational influences of other stars, nebulae, and even dark matter, which subtly alter its path over millions of years. This erratic trajectory makes the cosmic outcast a true nomad, never settling in one place for long. What's particularly intriguing about this rogue planet is the possibility that it might still carry traces of its original system. Elements and compounds from its early days could be preserved in its icy crust, offering scientists a rare glimpse into the conditions of its birth. By studying these remnants, researchers hope to piece together not just the story of the cosmic outcast, but also the broader history of planetary formation and ejection. The cosmic outcast's journey is a testament to the unpredictable nature of the universe. It reminds us that even in the vastness of space, no planet is truly isolated. Each one carries the echoes of its past, shaped by the forces that set it adrift. As we continue to explore the mysteries of rogue planets, the cosmic outcast stands as a symbol of resilience and adaptation, a silent witness to the ever-changing cosmos. Next, we'll delve into how the ejection of this planet might have impacted its original star system, shedding light on the delicate balance that governs the birth and evolution of planetary systems. Stay with us as we uncover more about the ripple effects of this cosmic event. Now, let's explore the aftermath of the cosmic outcast's dramatic departure and how its ejection might have reshaped its original star system. When a planet is violently expelled from its home, it doesn't just vanish into the void, it leaves behind a ripple effect that can alter the delicate balance of its birthplace. In the case of the cosmic outcast, its ejection likely created a significant disturbance in the gravitational dynamics of its star system. Imagine a tightly choreographed dance suddenly disrupted by the absence of one key performer. The remaining planets would have to adjust their orbits to compensate for the missing mass, potentially leading to shifts in their paths around the star. These changes could destabilize the system, causing collisions, orbital migrations, or even the ejection of other planets. One of the most intriguing possibilities is that the cosmic outcast's departure might have triggered a cascade of events, reshaping the architecture of its home system entirely. For instance, the gravitational tug-of-war that led to its ejection could have pushed other planets into closer or more distant orbits, altering their climates and potential for habitability. In some cases, this might have created opportunities for new planets to form from the debris left behind, while in others, it could have spelled disaster for existing worlds. Scientists also speculate that the ejection of such a massive object could have influenced the formation of smaller bodies like asteroids and comets within the system. The sudden loss of a planet's gravitational pull might have sent these objects spiraling inward, increasing the likelihood of impacts on other planets. This could explain why some star systems show evidence of intense bombardment periods in their early history, events that may have been triggered by the loss of a rogue planet like the cosmic outcast. But the impact doesn't stop there. The ejection of a planet can also affect the star itself. The energy released during such a violent event could have caused the star to flare or experience changes in its rotation. Over time, these effects might have influenced the star's lifespan and the stability of its planetary system. The story of the cosmic outcast isn't just about a single planet's journey, it's about the interconnectedness of cosmic events. Its ejection serves as a reminder that every action in the universe has consequences, shaping the destiny of entire star systems. As we continue to study rogue planets like this one, we gain a deeper understanding of the forces that govern the birth, evolution, and sometimes the destruction of planetary systems. Next, we'll uncover the secrets of another enigmatic wanderer, a massive rogue planet hidden in the depths of space, waiting to reveal its story. Stay tuned as we delve into the mysteries of the hidden giant. Now, let's turn our attention to a colossal wanderer lurking in the shadows of space, the hidden giant. This massive rogue planet, only recently uncovered, has remained invisible for so long due to its incredible distance from Earth and its lack of light. Unlike planets orbiting stars, rogue planets like this one don't reflect sunlight, making them incredibly difficult to spot. They drift silently through the darkness, their presence betrayed only by the faintest clues. Detecting a planet like the hidden giant is no small feat. Traditional methods of finding planets, such as observing the dimming of a star as a planet passes in front of it, simply don't work here. Without a star to orbit, rogue planets like this one are essentially invisible to these techniques. Instead, astronomers rely on more subtle methods, such as gravitational microlensing. This occurs when the gravity of a massive object, like the hidden giant, bends and magnifies the light from a distant star behind it. Even then, the effect is fleeting and incredibly rare, requiring precise timing and a bit of luck to catch. Another challenge lies in the sheer vastness of space. The hidden giant is so far away that even the most advanced telescopes struggle to capture its faint signals. Its distance means that any light or heat it emits is incredibly weak by the time it reaches us. To make matters more complicated, rogue planets often blend into the background noise of the cosmos, making them nearly indistinguishable from other faint objects like distant stars or galaxies. Despite these obstacles, the discovery of the hidden giant marks a significant milestone in our understanding of rogue planets. Its sheer size suggests that it could be one of the largest rogue planets ever detected, challenging our assumptions about how such massive objects form and survive in the void. Scientists believe that planets like this one might have been ejected from young star systems during their chaotic early stages, or perhaps they formed independently in the cold, dark regions of space. The hidden giant also raises intriguing questions about the prevalence of rogue planets in our galaxy. If such a massive planet could remain hidden for so long, how many others might be out there waiting to be discovered? As our technology improves and our methods of detection become more refined, we may uncover even more of these elusive wanderers, shedding light on their origins and their role in the cosmic tapestry. As we continue to explore the mysteries of rogue planets, the hidden giant stands as a testament to the challenges and rewards of space exploration. Its discovery reminds us that even in the vast emptiness of the universe, there are still secrets waiting to be uncovered. Next, we'll delve into the cutting-edge technologies that are making these discoveries possible, revealing how we're pushing the boundaries of what we can see and understand in the cosmos. Now, let's take a closer look at the incredible tools that are bringing these hidden giants out of the shadows. The discovery of rogue planets like the hidden giant wouldn't be possible without the groundbreaking advancements in telescope technology. These cutting-edge instruments are pushing the boundaries of what we can observe, allowing us to peer deeper into the cosmos than ever before. One of the most significant breakthroughs has been the development of space-based telescopes, which avoid the distortions caused by Earth's atmosphere. Instruments like the James Webb Space Telescope, with its unparalleled sensitivity to infrared light, are revolutionizing our ability to detect faint objects like rogue planets. Unlike visible light, infrared radiation can penetrate cosmic dust and reveal the heat signatures of distant worlds, even those drifting far from any star. This capability has opened up a new frontier in the search for rogue planets, enabling us to spot objects that would otherwise remain invisible. On the ground, adaptive optics technology is also playing a crucial role. This system uses deformable mirrors to correct atmospheric distortions in real time, sharpening the images captured by ground-based telescopes. By compensating for the blurring effects of Earth's atmosphere, adaptive optics allows astronomers to achieve a level of clarity that rivals space-based observations. This technology has been instrumental in identifying rogue planets through gravitational microlensing events, where the planet's gravity briefly magnifies the light of a background star. Another exciting development is the use of wide-field surveys, which scan large portions of the sky in search of transient events, projects like the Vera-C. Rubin Observatory's legacy survey of space and time are designed to detect subtle changes in the brightness of stars, which could indicate the presence of a rogue planet passing in front of them. These surveys generate vast amounts of data, requiring sophisticated algorithms and machine learning techniques to sift through the noise and identify potential candidates. The combination of these technologies is transforming our understanding of rogue planets. By enhancing our ability to detect these elusive objects, we're not only uncovering their existence but also gaining insights into their origins and behavior. Each new discovery brings us closer to answering fundamental questions about how planets form, evolve, and interact with their surroundings. As we continue to refine these technologies, the future of rogue planet research looks brighter than ever. With every advancement, we're peeling back another layer of the cosmic mystery, revealing a universe that's far more dynamic and diverse than we ever imagined. Next, we'll explore how these discoveries are reshaping our understanding of planetary systems and their place in the galaxy. From the lonely wanderer to the hidden giant, we've journeyed through the fascinating world of rogue planets, uncovering 25 unique mysteries that challenge our understanding of the cosmos. Each of these celestial nomads tells a story, whether it's the frozen giant with its potential for hidden oceans, the dark wanderer influenced by dark matter, or the speeding bullet racing through the galaxy at incredible speeds. Together, they paint a picture of a universe far more diverse and dynamic than we ever imagined. These rogue planets remind us that space is full of surprises, from ancient relics holding clues to the early universe to binary systems defying the odds of survival. They push us to rethink how planets form, evolve, and interact with their surroundings. But as much as we've learned, the mysteries only deepen. What other secrets do these wandering worlds hold? Could some of them harbor life, even in the harshest conditions? And what will future discoveries reveal about their origins and their role in the galaxy? The search for rogue planets is just beginning, and with every new discovery, we're rewriting the story of our universe. So, what do you think lies ahead in the study of these enigmatic worlds? Share your thoughts in the comments below, and don't forget to subscribe for more deep dives into the wonders of space. Hit that notification bell so you never miss an update as we continue to explore the mysteries of the cosmos. Thanks for joining us on this journey. Until next time, keep looking